On behalf of Institute of Engineers, Pune Local Center, myself, Chairman KK Ghosh, and on behalf of NDRF, I welcome you all for this lecture on Visualizing Flow, Seeing is Believing by Dr. KT Madhavan sir, Technical Advisor of NDRF. This is the 6th lecture we are conducting on the aegis of Aerospace Division Board of the Pune Local Center. We have started with the 8th May, the first lecture or webinar was there on the 8th May, where the career opportunities was there, career opportunities in defense and aerospace sector, and followed by number of lectures. In between this, we have gone for one all India webinar on startups in the aerospace and defense sector. And this is the second lecture we are, or webinar invited talk we are conducting in association with the NDRF, one of the fora of IEI. So I welcome you, Dr. Madhavan sir, on this, and also welcome Dr. Ramachandran and all the students, all the participants, various engineering colleges. So I now request Mr. Mukund Kumar to introduce give the brief about the NDRF. Mr. Mukund Kumar.
Thank you, sir. Yeah, thank you, sir. Before the starting, I would like to say something about the NDRF. So National Design and the Research Forum is a 50-year-old organization. NDRF promotes research, design, and development. The objective and the purpose of NDRF is to promote and advance the science and practices of design in all branches of engineering. Dr. Mayalswamy Annadurai, and also known as the Moon Man of India, is the chairman of NDRF, and Dr. V. Dilip Babu, scientist F grade in DRDO, is the director of NDRF. Under the leadership of our chairman and director, Dr. Mayalswamy Annadurai and Dr. V. Dilip Babu, in NDRF has started many programs. For the student section, NDRF has started online mini project scheme, techno spotlight event, internship program. In mini project scheme, NDRF gave an opportunity to engineering students to complete their innovative project under the expert mentor. The mentor may be the scientists, engineers, college professors, technical advisors of NDRF. After the successful completion of online mini project scheme, NDRF provide e-certificate to the student. Recently, NDRF has started Techno Spotlight event. In this event, NDRF gave a platform to show the innovative projects in front of scientists or subject expert. The student present their presentation in front of expert panelists. They can also discuss the project modification. Technical support can also be provided by the NDRF if required. In this platform, NDRF gave an opportunity to startup team which associate to the institution to present the presentation and their innovative work. For all technical activities related to NDRF, and please visit National Design and Research Forum website. And you can also see 14 days online internship program in our YouTube channel. Recently, we have completed our 14 days online internship program in July. So with these words, I want to wrap up my speech and hand over this session to sir. Please, over to you, sir.
Thank you, Mukund, for giving the brief introduction about the NDRF. I request all the students who are joining, they can go through the NDRF website and they can take the opportunity and they can discuss, and the email address and everything are given, whatever their requirement is there, they can discuss with that online, so that you will get the help from the NDRF regarding the aerospace curriculum or whatever it is there. Now I request our student coordinator, Rinisha Nikhade, to brief about the today's program and introduce our today's guest speaker, Dr. KT Madhavan sir. Rinisha, please.
Sir. So good evening, one and all present here. I, Rinisha Nikhade, as student coordinator, welcome you all for this virtual webinar, which is on visualizing flow, seeing is believing, by Dr. Madhavan Sir. So here I want to give rough idea about what is visualizing flow. So in fluid mechanics, flow visualization is utilized to make flow patterns visible in order to get qualitative or quantitative information about them. Dr. Madhavan Sir, our evening speaker, will discuss flow visualization, its relevance and applications in further detail. So now I would like to give an introduction of our today's evening speaker, Dr. Madhavan Sir. Dr. Madhavan Sir earned his MSc at worked as a scientist at National Aircraft Laboratory, where he was involved in research and development on the development and uses of aerospace instrumentation. For his work in techniques, he received a PhD from IISc Bangalore. Sir work at NAL included work in advanced flow diagnostic techniques, flow control, signal processing, unmanned aerial vehicles, solar energy, and other areas. He joined CIMAT, where he works to promote operations. Dr. Madhavan Sir was awarded the AR and DB Silver Jubilee Outstanding Performance Award for his work on LDB measurements in turbulent jet and separated flows, as well as the NAL Award for Outstanding Performance in Research for his work on successful application of two-component LDB to the documentation of axisymmetric separated flows. Dr. Madhavan Sir got 5 papers published in international journals, 5 articles were published in national journals, papers both in international and national conferences. His research interests include analog and digital instrumentation, digital signal processing, unmanned aerial vehicles, MAPS, smart materials and structures, and solar cell applications. We are glad to have you, sir, today. Before handing over this webinar to our expert speaker, I would like to request each and everyone that if you have any queries or question, you can post it in the chat box and the question answer session will be conducted at the end of the expert talk. Now, I request our today's expert to take a lead. Over to you, sir.
Thank you. Thank you very much for your kind words. Say, I'll share my screen now.
Yes.
Yeah.
Can you see it now? Can
Yes,
you
sir.
hear it?
Yes,
Yes,
sir.
sir. Yes, sir.
Yes. Okay,
Yes.
fine. Okay, all right. Thanks again for the kind words you have spoken about me. Okay, now, as you know, like any other technical subject, any other scientific work, it's important, it's very important to know, about the characteristics of the phenomenon you are trying to investigate. So like in this aerodynamics also, it's important to make an initial assessment to find out the characteristic, what the flow is like, what are the parameters of interest. So how do we do this? If you want to do quantitative measurements with the complex instrumentation, it takes long time and you can't make a very quick judgment about the characteristics. So how do you really do that? It's here that visualizing the flow and seeing the flow itself comes into picture. So it's a very sort of huge topic, big topic, and I don't think I can do justice talking about the entire thing. I will give you only a gist of the the technique and what is flow visualization. So the outline goes like this. I'll just introduce the topic and really tell you how do you really visualize or see a flow. How do you do that? So we'll see that how it can be done. And what are the advantages of the technique, flow visualization? And I'll make a quick comparison between quantitative flow measurement techniques and our qualitative methods of flow visualization. Then we'll see important aspects of aerodynamic flow visualization. And flow visualization has many applications, not only in aerodynamics. I mean, not only in the aerodynamics of flows. It also is very important the hydrodynamics. It has many applications in civil engineering, and I'll also give an exposure to some modern technique like shear sensitive liquid crystals, which I have worked for some time. And the fact is that it was so I have only very short time. Within 1 hour, I have to finish all. So I'll make a very brief introduction to these things. Now, as you know, most of the fluids, air, water, whatever it is, are transparent, and their flow patterns are rather invisible to us with the naked eye. So how do you do the eye catching? How do you do the visualize the motion and its interactions of the fluids with the surroundings? There are many ingenious techniques developed for this eye catching. How to visualize this and their interactions. So in flow visualization, the flow pattern itself is made visible and can be observed directly. You can see it actually, or in the video, it can be seen photographed, or you can record it in a camera. Now, as I told you, it has many advantages. It doesn't require the complex circuitry or complex instrumentation, because expensive and difficult to set up. Then you can make up set up a quick qualitative checks. Now, instantaneous information over the entire flow field, is available. When you make the normal conventional measurements like the hot air or LDV, you get only point-wise information. With the flow visualization, although it's qualitative, you can get the information, the vector information or velocity information, flow characteristics over the entire field. That itself is very, very attractive because you get a quick result. Then you can start your mathematical modeling work, or you can do the computational work. You can start the measurement work. So that way, flow is easier than the quantitative methods. So it helps in understanding the flow phenomena. Now, what are the methods? What are the types of methods? What are the equipment? What are the methods used for flow visualization? For gas flow, we have what you call surface flow visualization, wherein oil, particles are mixed with an oil, and the small dots are put on the model surface or surface of interest. With the flow on, you take the photograph. Second thing is silk tufts, very thin, small, short silk tufts are pasted or glued on the model surface, and with the flow, the pattern itself is recorded. Then there is much more attractive method called smoke flow visualization. Now, the entire flow field or the model surface, for example, is illuminated with a flash lamp or an LED lamp or a laser, and you let in smoke or fog as tracer particles. You can take a video, you can do a video recording of the flow, or you can take still pictures of the flow, which will reveal the qualitative information of the flows. Then for high-speed flows, compressible flows, you have shadow graphs. You also have schlieren techniques for compressible flows. For liquid flows, we have injection techniques. What you do is you inject a dye, color dye, or particles, or hydrogen bubbles, or air bubbles, or you make the flow fluorescent, and when with the flow on, the fluorescence, the changes, and then you can get the flow pattern easily. Seeing is believing. Yeah, I just want to tell you this. Say, when you look at a car, when you go in a car, with your eye, you see nothing. You see nothing over the flow. Now, when you really visualize that, you will be thrilled to see that this is the pattern. This is the flow the flow pattern around the car, which you can never imagine. Or look at this beautiful phone Carman vortex tree. I hope you have got aerodynamics background, right? You can all of you can understand what is phone Carman vortex tree, vortex breakdown, or vortex spreading, etc. So this is a beautiful picture of phone Carman vortex street behind behind the wake of a circular cylinder at very low Reynolds number, and it's beautifully pictured. Look at the third picture. Can you ever imagine a hurricane looks like this? Because we see this in TVs nowadays, but unless you just do the visualization, you can know. Of course, this is natural visualization. Nobody has done any visualization. It's taken from probably a helicopter or a plane, from which you could see the pattern of the flow in the hurricane front. Look at this fourth one at the trailing edge vortex shed on the wingtip of a flying aircraft. You can never believe unless you see that this is the kind of flow around there. Make a quick comparison between qualitative and quantitative methods of flow measurement. Now, what first thing comes to mind is the easiness of setting up. As I said earlier, it's easy to set up a simple flow visualization setup compared to a quantitative measurement instrument. You don't need any great expertise or skill. You need some skill, you need some technical skill, but you don't need to be an engineer himself to make a flow visualization setup. On the other hand, if you want to make quantitative measurement, find LDV or PIV or hot wire thermometer, you need some understanding and your engineering background. Easiness of operation. Flow visualization setup is easy to operate. On the other hand, there are complexity of operations with any of the non-intrusive or non-intrusive measurement techniques in quantitative scale. Quickness of the results. You can almost immediately see the results, almost immediately see on the camera or recorded pattern of the flow in the case of flow visualization, qualitative checkup. In many cases, on the other hand, quantitative, it takes some time to get the data recorded, analyze the data, and get the necessary information on the flow characteristics. Quantification of results is much easier with the flow visualization, although it is limited and takes a longer time to obtain the quantified data from a flow visualization. Then, of course, mathematical modeling, you can have a quick verification of the modeling with the flow visualization data rather than an experimental, quantitative experimental data. This is the gist of the comparison between qualitative and quantitative methods. We'll come to the actual visualization now. Now, as I told you, there are in surface flow, the method, first method I told you, I mentioned was visualization of the flow on the surface of the model. Now, there are two methods popularly used, as I mentioned. One is tuft method. As I mentioned, the silk tufts are placed on the model, and you get the flow pattern recorded when the flow is on. You can see that tuft on a delta wing on the left side, tuft flow visualization picture. In the second method, what you see, the oil flow visualization on the right, you mix fine powder of titanium dioxide or fine aluminum powder, etc., in an oil media. Typically, it's oleic acid or SAE grade 32 vacuum pump oil, or sometimes people use turpentine too. Now, so mix this for some time, finally mix it, and then mix my small dots put small dots on the surface of interest, and leave the flow on for some time. You get the nicer pattern on what you have shown in the right side. Surface oil flow visualization has terrific advantages. on trying to see how a flow separation takes place, flow separation and famous flow separation and reattachment. You look at this on the image, surface oil flow visualization catches or captures the streak lines formation on surface due to shear force acting on the discrete oil dots. See, you have put the oil dots over there, and because of the shear force acting on the oil dots, you get a fine, nice picture which indicates the onset of separation, and then the point of separation line, the dead air region between the separation and the separation and the reattachment point, and finally the vortex dominated reverse flow region. So you can clearly see flow getting separated, then the dead air region, reattachment, and then finally the vortex dominated reverse flow region, as I've clearly shown this. So this gives you fantastic information before you start any actual measurement or mathematical modeling. This can give you terrific information much faster than a quantitative measurement. Smoke flow visualization. So as I mentioned, smoke is let into the tunnel, wind tunnel test section where you have the model, but you need an illumination. And as you can see, this is a typical setup for smoke wire flow visualization. The main components are the tunnel, of course, test section, and the top of the tunnel, usually, except for illumination, you leave the whole thing blackened so that the light will not get reflected from there. Then your external light will not pass into it. Then the camera or the sensor is mounted on a frame, and on the frame also there is a heating wire, as you can see, which is usually a tungsten corrugated wire, for which about 120 volts is passed. Of course, one can control that, and depending upon the requirement of the smoke you require, you allow the voltage. You let in the voltage. Now, as you can see on the right, there's a smoke fluid, which is usually paraffin oil filled in that, and it's pressurized. So what happens is, when there is a pressurized paraffin oil falling over the corrugated wire, it gives you out smoke because it's heating wire with the paraffin oil dripping over that with a gravitational force. You get a smoke in that, because now with the flow you can get the flow pattern as you can see I'll show you in the next slide. We did several studies. One of them which appealed to me was the flow visualization studies on an Epler 61, two models, two low Reynolds number airfoil models. One is Epler 61 and the other one was SM4308 airfoil. Now, as you know, you need to do flow control for the good performance of a wing or of an aircraft or an airfoil. One should do the flow control and remove the LSB. You know what is meant by LSB? Laminar separation bubble. Laminar separation bubble causes a lot of problems. Drag, separation, reduces the stall angle, etc., because once the laminar separation bubble sits on the wing of the aircraft or a airfoil, the stall angle comes down considerably. So you need to have some method by which you can control or mitigate the effects of the laminar separation bubble or flow separation. So, but how do you decide? How do you go for the separation control? There are many techniques to do the separation control, but the main issue there is where exactly to locate the what is the optimum location for placing the control device. Now, friend, as you see in the next two slides, I'll show you the effectiveness of the flow visualization to locate the place where you have to keep the control device. Now, I've given the other details. There are two airfoils. There's the tests were done in a 0.2 by 0.2 meter by 0.2 meter test section of tunnel at two Reynolds numbers, 6.7 10 power 4 and 8.7 10 power 4 at incidences of 4 degrees, 6 degree and 8 degree. And these are the beautiful pictures on the A+61 airfoil. What do you see here? What you see here is three angles of incidence, 4, 6 and 8 degrees at a low Reynolds number of 67,000. The flow separation takes place around about 60% of the 60 to 70% of the chord. But as the angle, as alpha increases, this point of separation moves further upstream near the leading edge. Again, as alpha increases, it goes much further upstream. On the other hand, in case of the Reynolds number is increased to 87,000, because the flow has some inherent strength, the effect of laminar separation bubble is felt much less, and the separation bubble height and width is much smaller. Now, we studied also, as I told you, SM4308 airfoil, where we saw that laminar separation bubble occurs at 25% of the chord and reattaches at 50% of the chord. Now, flow patterns, as you can see in the next, clearly show that length of the LSB reduces and height improves with increasing angles of incidence, as shown in this. This is a much better picture we got. We are very happy to see such a nice flow visualization pictures. These are again, as I mentioned, at two Reynolds numbers 67,000 and 87,000 at three angles of incidence. What is important to note is that the amount of effort required is much less compared to a quantitative measurement technique like LDV or a particle image velocimeter. This is a old picture on the top view of a delta wing studied in a water tunnel and a cross-section view of flow visualization of delta wing. This is a beautiful picture of the tip vortices on a delta wing, front top and side views. Very, very, very attractive to see that. And if you wanted to if you want to measure these tip vortices and visualize that, it would have taken an awful lot of time. This is a very old picture of Von Karman vortex street in the block body wake, in a cylinder, the wake of a cylinder, using mixable lightweight fine aluminum powder. Beautiful pictures. It's not a smoke flow visualization picture. You may think that it's a smoke flow visualization picture, but it's not. It's a very nice surface flow visualization picture, expertly done. This is flow around a delta wing. First one is done by double delta wing, actually. Double delta wing done in the water at 15 degrees. Actually, the photograph is not color. So the color streak fine method, which I have written there, is irrelevant. It's a black and white picture of a color photograph. And then using suspension method, we are the flow is flow visualization realized on a double delta wing. Now I'll go, instead of air, we'll go to the hydrodynamic flow visualization techniques. The idea is that you have to go to much lower speeds to get finer patterns. To get the finer patterns like what we see in left and right, one, the swirling flow behind an inclined cylinder using dye lines in a water tunnel. Very fine pictures, and you can make a lot of sense out of that. Similarly, swirling flow, dye injection method to realize swirling flow behind an inclined rocket model. Now we will go to another method or another concept. Now, this is for compressible flows. Now, what you have seen so far is generally for low speed flows, low Reynolds number, compare relatively low Mach numbers or no Mach number, very low speeds, about maybe 10 meters per second to 30 to 40 meters per second. So such flow visualizations can be done for incompressible fluids, using those techniques like smoke flow, etc. So when it comes to high speed flows, compressible flows, where Mach numbers start from the transonic to the high subsonic, high supersonic, these methods, smoke flow visualization, cannot be applied because the smoke will diffuse and we will not be able to get any clear picture of the NM. But we have two methods which I'm going to show. In fact, I'm going to show you three methods by which you can get conclusive results about the flow parameters or flow characteristics under compressible flow regime. Now, one is what you call a shadowgraph. It's a simple technique. You have a small light source and it's illuminated a parallel beam or many parallel beams are derived from a small light source using two convex lenses. The output, the beam is, again, the light is focused on a camera using a small convex lens. Now, the model is kept inside the test section and it's illuminated by the light source. It could be a laser, it could be a white light or whatever it is. But what happens is important. Now, the shock waves, when it comes through, it will cause density variation. Density, there, one of the characteristics of a shock is that it causes in a compressible flow, it causes density variation. And what will happen when there is a density variation in any fluid or in any the medium air? It will change the refractive index of the fluid. Now, because of the change in the refractive index of the fluid, there will be a dark pattern because the light will not, you cannot get the light in the camera. So there will be a dark pattern. So as you can see on the right side, a bullet at supersonic speeds can, and the bore shocks on the right side is derived through, it can be pictured or can be photographed depending upon the refractive index change induced by the shocks. Now we will go to another more elegant and little more precise technique called schlieren photographic technique. Now, in a schlieren photographic technique, as you can see, there's a light source and it's passed through a narrow slit to make the beam as narrow as possible. As you can see, there are two concave mirrors. One is illuminating the test section, which contains a model with many fine lines of light, and the reflected light collected by a concave mirror again, it falls on a knife edge and finally on the camera or recording device, whatever it is. So what happens now? When there is a refractive index change, the lines, the optical lines or the optical path gets shifted, and the knife edge will prevent the light from falling on the recording device. So much so that there will be a dark patch. So corresponding to every shock, shock wave, there will be a dark patch recorded by the camera. Now, this way, you can alternately, record the flow pattern with the shock and without the shock. These two are two recordings. One is a cone cylinder supersonic free flight at 12.5 degree semi-vortex angle at Mach number 1.84. The other one is a shock-free forebody. What you can see is the forebody doesn't have a shock. So how do you really, the bow shock has been shifted towards the afterbody. But this, how do you really see such pictures? How do you really make a judgment that where the bow shock is, or where the other shock, a cone cylinder in supersonic free flight, where the shock waves are coming? It's only one way is to do either shadowgraph or schlieren techniques. Shear sensitive liquid crystal. I used to joke, I did some work before I retired. I did some work using shear sensitive liquid crystal. So I used to say that after my PhD, I have been doing SSLC. This is a very attractive technique, and there are a lot of difficulty. There is a lot of application skill required to do this, to apply this technique. That's why it has not become extremely very popular. But we did some experiment. We did, excuse me. We did some experiments in a supersonic tunnel at the 2 Mach numbers. And in fact, 3 Mach numbers: transonic, 1 supersonic, and 1 high supersonic. Now, the basic principle is very simple. Some of the cholesteric liquid crystals have a property with the shear force acting on the when the liquid crystal is applied, when the liquid crystal is applied on a surface, model surface, with the shear force acting on that, the color of the liquid crystal changes. Now you may ask, why is it changing? The reason is that it's a nice part of the physics. What happens is the orientation of the lattices in the liquid crystal changes. So normally they are all disordered. Now when there is a shear force acting on that, shear stress acting on that, the orientation changes and they get nicely oriented. So the reflected light frequency goes higher from a nicely oriented liquid crystal. There will be fine, the high frequency reflection. On the other hand, if they are randomly oriented, if the lattices are randomly oriented, you will get non-coherent data, but at a higher wavelength and lower frequency. So corresponding to lower shear stress, you will get a red or maroon. Corresponding to the highest shear stress, you will get blue color. So you can calibrate the measurement. You can, depending upon the camera angle and the color, you can do the processing and get the quantitative shear stress information on a model, or in a medium like this, in a jet, for example. You see, the shear stress vector field in a jet is generally symmetrical, in an axis symmetric jet. And this was further verified by checking magnitude of the shear stress, by attributing different colors of that. And they also did, these authors also did a quantitative measurement. So what they could see that the symmetrical distribution and the highest shear stress in the center line. And of course, as you go away from the center line, you can reduce shear stress. This I have shown you, but only to show you that the application, there are fantastic applications of smoke flow visualization for vehicle aerodynamics. As you can see this, we have the, not me, I have taken this from a famous book called An Album Flow Visualization, which I will give the reference at the end of the talk. So the first one is a wake behind an automobile with tuft method, which I talked earlier, tuft grid method. Tufts are placed, in a matrix, in a given matrix, and with the flow, you get the distribution of the velocity or the pressure on the second one around. Now this is slightly different. they have used fluorescent, applied fluorescent dye on the tubs. And with the illumination, you get a very nice flow pattern on the car or Jeep, as you have seen on the right side. And let's make what you see on the left one is again tuft method, and flow around a super express. I think it's a train, and with the surface tuft model method. So tuft method is shown in the right side. This you all have heard about the MEMS, microelectric devices, and now they can be used for vortex control. It's a flow control device, and how effective it is for the vortex control is demonstrated by the flow visualization, as you can see it in this picture. Coming to industrial aerodynamics or building aerodynamics or applications of flow visualization for civil engineering, we did a work for some undergraduate students, civil engineering students. I was also involved there. Now, how to see what is an optimum shape for a building? Now, we need to get a tall building, and then we need to optimize. What would be optimized shape where the drag or the wind forces are minimum, so much so that building stability and the building stability is there for a very long time. So we took 4 models. One is a rectangular model on the left side. Then you have a what do you call a setback model. That means there are 4 openings on all the 4 sides. Then there is a chamfered model and also the corner smooth model. So what gives you, which one is the most effective to give you the least drag or least effect of the wind is what we checked in our wind tunnel. We did quantitative measurements also, but I will show you, since it's a discussion of flow visualization techniques, I will show you the flow visualization pictures. So in the first one, left side, you can see silk tufts, different color. It was not necessary to use different colors, but we could get only, the silk threads with this color. So it was also nice to, put the silk thread with these colors. So what you see on the left side, this is the wake. This is the near wake of a building, which has what you call setbacks, 4 setbacks. Now, aerodynamically, since there are 4, forward-looking and forward-facing and backward-facing steps, the disturbances and the unsteadiness has considerably increased, as can be seen from the tufts. These tufts are in random directions. They are oscillating. Of course, I don't have a video, otherwise I would have shown you the video. Unfortunately, I don't have the video right now. These were oscillating in all sorts of directions, and because of the unsteadiness of the flow. Coming to the next picture on your right side, it's a rectangular model. Because there are no backward, there is only one forward facing and backward facing step. The flow is much more steady. So the reverse flow components are much less in this. So as you can see, the steadiness of the flow has increased. Now, we tried chamfering of the building. Many buildings you see like this of the shape, chamfered shape, but this also has, because of the steps faced by the flow, there is still unsteadiness, as you can see there. And finally, we tried a smooth cornered building where all the 4 sides of the building are cornered. Aesthetically, does it look good or not? That is not the issue here. But it is more stable. There is much less drag. Wind flow is much less effective, and the wake is much more steady. Unsteadiness is much less. And also, the pollutant agent, etc., will not be, stagnated in the near the building. So that's the idea. By what we found is that the best optimum shape from what we did was corner smoothed building. So this seems to be a good application. We did some, to get the conclusive data. We did indeed some drag measurements also, force measurement also. In the liquid flows on the molar surface, you can see flow over airfoil and with particle visualization. And shown you with the dye visualization, the rocket wake. Interesting. Insect walking inside small, water or liquid. These are what you might have heard about the creeping flows. Very, very, very low Reynolds number, very low speed. It's like mm per second. But with the ingenuity, this author has recorded this fantastic path or trace of this insect walking on water. Beautiful, really very beautiful. It takes a lot of effort and time, but to be appreciated. Jets and plumes, beautiful pictures. One is top left, you see, is the flow below an ice cube in water, near field of a jet, which you have seen number of times earlier, and a flame, a jet and flame, how it looks visualized. I would like to show you one video. I don't know if it works. Okay. 1 second, please. I hope I can play this video. Yeah. This is a video of a hump placed in the wind tunnel. See how beautiful the wake and the forward, everything is traced. This is enjoyable. This is what you call seeing is believing. So, can you hear me? I suppose. I hope you can hear me, right? Hello, hello.
Yes, sir.
Yeah.
Yes, sir.
Can you hear me? Okay. Now, I think I would like to stop here, conclude my talk here, saying that visualization is a very important tool which finds immense amount of applications in experimental aerodynamics, not only experimental aerodynamics, many other branches of engineering, hydrodynamics, flow visualization in water tunnel, flow visualization of buildings and bridges, and so on and so forth. A variety of techniques are available today, and a variety of techniques are being developed, as the days go. Like any other field, techniques are being newer and newer techniques are being developed. Qualitative information of the flow characteristic can be extracted very easily, but quantitative information also is possible. I have not shown you, except for shear sensitive liquid SSLC. I have not shown you how to extract qualitative information from this, but it's quantitative information from this. It's quite possible to get, the streamlines and the, other quantitative information, but it needs some little effort compared to the other measurement technique. Modern techniques being developed for quantitative flow visualization. I'll call it quantitative flow visualization because you have a flow visualization qualitative, but you get the quantitative information from this. That's why we call it QFV or quantitative flow visualization on the whole field. See, point measurements will give you only the information at a time, and they give the information and the time reference. You lose the time reference there. See, the comparison is between a Lagrangian frame of reference and the Eulerian frame of reference. So whole field information without time lag can be given from qualitative techniques like shear sensitive liquid crystals, planar, PLIF, it's called planar laser induced fluorescence, pressure sensitive paints. I have not talked about it. I thought I wouldn't have time, but now I feel that there is enough time, but I don't have slides. Otherwise, in the next time, I'll talk about a very interesting topic called pressure sensitive paints. There again, certain paints will respond to the pressure changes, and using based on what you call oxygen, partial pressure of oxygen being quenched. So you can get the pressure information on a surface, whole field pressure information. Again, using feeder tube or devices like that, you can do point measurements, but not so with this. You can get the entire information of a surface, a pressure information of a surface using techniques called pressure sensitive paints, which has become very popular. There are a lot of work going on in ISRO, National Aerospace Laboratories, and many other laboratories using PSP. And actually, this was developed in a German aerospace laboratory, DLR it's called. So that we adapted here, and then it has been very successfully applied to many problems for many problems of interest to ISRO, DRDO, and NAL, of course. Then there is one thing called BOOT, background object optical tomography technique. But again, these are all totally different applications, and then if you want to go through each and everything, it takes very long time. Many more techniques are there in the flow visualization, and then I have given a list of references in the end. I think since this meeting is recorded, I hope you can pass on the references. You can get the references which are given at the end of my lecture. I very strongly recommend that all of you go through the reference one, which an album of fluid motion by Milton Van Dyke. Fantastic. Some of you might have seen that. But those who have not seen that, it gives you a terrific, good picture of the many kinds of flows in the nature. You will be impressed, very impressed. And these are all the references. Some of them are the work done by us in NAL, and some of them are. So now I will stop here, and the session is open for questions and answers. I do not know what method will you flow in the chat box if there are
Yes,
questions.
sir. Yeah, chat box. Somebody will, Renisa will, they'll take
Yes.
one
Okay.
questions and
Now
they'll ask.
there are, these are. I'm not an expert in this field. That I must.
No, you are only answering somebody.
Whatever is possible, whatever
Yeah.
is your question, which I can answer.
Yeah,
I will do it right now, or otherwise I will send it through
No,
your email.
definitely.
Fine. Okay. Please go ahead.
Renisa,
Thank you,
please.
sir.
Yeah.
Thank you, sir, for such wonderful webinar. So there is a question that any flow visualization techniques for fraud numbers in surface open channel flows
I'm not.
undeveloped, sir?
I'm sorry. I'm not. I didn't get you. Tell me again, please.
Yes, sir.
Yes, sir. Any flow visualization techniques for fraudy numbers in surface open channel, irrigated areas, civil engineering applications
We
are
can.
developed?
Yeah. We can flow visual. I think we can use. We can use two methods. One is one is using the laser-based illumination. You use laser-based illumination and inject particle, either dye or a particle, into the flow, into the flow in an open channel, in an open water channel. We have tried to do something in the college where I was working for a civil engineering department in fluid mechanics lab, but somehow it didn't go through. But I'm sure, I'm very convinced that in this case, you can use dye or particle. And it's important that you should use illumination with the laser. With a normal light source like LED or flash lamp, it will be very difficult. Flash lamp first because it will heat the flow, and again the parameters will change. So best thing is to use a laser illumination and use dye or particle. It's possible, definitely possible.
Okay, sir. Thank you so much. The next question is, if we wish to find the exact location of a flow separation over a finite wing model at a certain flow condition, then which is the best flow visualization, oil or a smoke?
Flow visualization, as I told you in the beginning itself, it's only a qualitative technique. You are not pinpointing, you cannot pinpoint the location of the separation or reattachment exactly. That has to be done through either techniques like particle imaging velocimetry. I hope you must have, your aerospace students, you must have heard about particle image velocimetry, or point-wise measurements like laser Doppler velocimeter. So, or even sublimation. So these point methods will give you exact pinpoint location of where the separation or reattachment takes place. And also it depends on the flow regime. Is it a high-speed flow? Is it a Mach number again greater than 1? Then the smoke method, etc., will not work there. Then you'll have to use, if at all, you have to use only shear sensitive liquid crystal. Shear sensitive liquid crystal in all these things is very, very promising. You can get the exact pinpoint the location of separation, which I have done. We have done some work on that. You can also additionally, as a bonus point, you can get the shear stress also. As aerodynamic students, aerospace students, you all know that there are not many techniques available today. It's extremely difficult to measure the surface shear stress, not in the open, not with the free shear layer. On the surface of a body or a model, it's extremely difficult to measure the shear stress. So if you use techniques like SSLC, this can be done. I think that's the answer, I hope. I don't know. Have I answered your question? I don't know.
Yes, sir.
Okay.
Yes. So questions are over. Since we are also aerospace students and we are the final year, so we have this subject experimental aerodynamics, and this webinar is very helpful to us, sir. Thank you so much.
Oh, it's my pleasure. I only think is that I could have continued for some more time.
But you thought the number, the sufficient time was there with you.
Maybe I'll get another chance. I also want to talk to you about pliff and other things which I didn't do, sublimation technique. There are many more very interesting techniques which again, it's positive time, and one evening you cannot really tell you. It's a broad state.
Yeah. So I think and hope that we are good for now. So I will proceed with a vote of thanks. So I, Rinisha Nikhade, as a student coordinator on behalf of REI Pune Local Center, MIT University, and the whole fraternity, would like to express my heartfelt gratitude to Dr. Madhavan sir for an insightful and educational webinar. Today's webinar was packed with information and interesting facts. I'm confident that the invaluable information provided by sir would be beneficial for our studies and future. I would also like to thank the Mukund sir. I would like to thank Dr. Ghosh sir, REI member, Aerospace Engineering Division Board for his assistance. Dr. Sunil Dingre sir, HOD of Aerospace Engineering Department from MIT University, as well as all the dignitaries from various institutions for their efforts, and all the student coordinator members for their tremendous collaboration. I want to express my heartfelt appreciation to everyone in the audience for their support. Thank you, everyone, and have a great evening.
Thank you, Madhavan sir.
Thank you.
Nice.
Thank you
Yeah,
all. Take
definitely.
care.
Thank you. Take care, sir.
Stay
Yeah.
home
Yeah.
and be safe.
Yeah. Thank you, sir. Thank you.
Yeah.
Thank you, everyone. Yeah.
Thank you. Bye-bye. See you.
Bye.